Hello and welcome everyone. This is the webinar about the use of integrated surface and groundwater models for hydrological studies and aquifer recharge estimation. It's offered by Water Services and Technologies, and it will be presented by me, Christian Price. So, getting into the main subject of our webinar, let's start our conversation here talking about the water cycle. I imagine that most people have seen a picture like this one a lot of times, but I think it's really important to have the information that this picture shows in your mind, like when we're talking about water cycles, when we're talking about hydrology or hydrogeology, because this picture shows us that what happens on the surface is always connected with what happens underground. So we cannot talk about hydrology without thinking about what happens underground, and also we cannot talk about what happens underground without thinking on what happens on the surface, because we can see that all the water cycle is connected. So the water in the ocean is connected to the groundwater, and the groundwater is connected to the surface water, which is connected to what happens on the atmosphere. So it's always important to have in our minds that the water has a cycle and everything is connected. Another thing that I think it's very important to have in mind when talking about integrated model is the distribution of water in our planet. From all the water that we have, only 2.5% is fresh water. From this 2.5, about 70% is trapped in glaciers and 30% is underground, represented by the groundwater. And only 1% is surface water, is the water that we see on the surface. So a message that this information gives us is that we cannot talk about fresh water only thinking about the water that we see on the surface. We need to know that most of the water is in glaciers, and another great part is groundwater. So we need to have good practices on water use, considering not only the water that is in the surface, but also groundwater. We're going to talk now about the definition of integrated modeling of groundwater and surface water. So we have here a picture that represents a random watershed. And here we're going to talk about all the cycles that we have, all the interactions that the water have in a watershed. So we have on the surface, we have precipitation, we have interception by the trees, for example, and we have infiltration. We have also the surface runoff. We have evapotranspiration on the surface from water, for example, that gets trapped on the leaves of the trees. We have the evapotranspiration also from the water that the plants capture from their roots, and we have the water that the plants use for their growth. And we have also the lateral flow on the first layer of the soil. We have the lateral flow, which is the water that infiltrates but flows directly to the main streams and don't have any connection with the aquifers. We have the groundwater discharge, which is the interactions between the streams and the groundwater. Also underground, we have the aquifer recharge, which is all the water that infiltrated and got to the aquifers. We have the changes on the water table, and the water table changes seasonally. And we have the groundwater flow. If we want to study what happens underground, we have the hydrogeological modeling. And for example, we have MODFLOW, visual MODFLOW, we have model muse, we have VFlow. Some models represent only what happens in the saturated zone, for example, MODFLOW. And other models represent also what happens in the unsaturated zone, for example, VFlow. If we want to study what happens on the surface, we have the hydrological modeling, for example, HMS, MIKE-Hydro-Basin, SWAT, and MIKE-SHE. Again, some models, they study only what happens on the surface, like HMS, and other models study also what happens in the unsaturated zone, for example, SWAT and MIKE-SHE. Finally, for integrated modeling, if we want to study everything, all these interactions, we have MIKE-SHE, we have SWAT-MODFLOW, we have PARFlow, GSFlow, MODFLOW on water, and all of these models, they study all these interactions. And what's the importance of integrated modeling? For example, if we are talking about hydropolitics, we are studying water resources management. The use of integrated modeling is essential for planning the use of groundwater and surface water. We cannot have a good program on water management if we look only at groundwater or at surface water. We need to study both of them. And also for land use planning, the land use affects both the surface runoff and also the infiltration. So it affects the surface water and the groundwater. And we're going to talk a little bit about this later on this webinar. If we are talking about hydrological studies, shallow aquifers have greater influence on the surface runoff and surface storage. And hydrological models, they have limitations on predicting what happens in the surface water when we have shallow aquifers. Also, integrated models, they represent better the interactions between streams and the aquifer. So, for example, if we are studying a drought period or a flood period, the integrated models, they can have more realistic scenarios. And on hydrogeological studies, the use of integrated modeling is essential for the refinement of a very important input data, which is the aquifer recharge. So talking a little bit more about the aquifer recharge, as I just said, is a very important input data on hydrogeological models. And often the estimation methods that we use for aquifer recharge on hydrogeological models, they are simple. They don't consider changes over time. And the aquifer recharge is affected by many different factors, such as changes on precipitation time series, different permeability between different land use, for example, urban land use or agriculture, soil moisture, soil types, and plants growth, and water table changes. And only complex hydrologic and integrated models consider all these factors and physical processes that have great influence on the aquifer recharge. If we use a hydrogeological models, they don't consider all these factors. So that's why we need to give the model the information on this input data, the information about the aquifer recharge. So now I'm going to show you a case study on the influence of land use on aquifer recharge. So this case study was held on the Itajaí River Watershed, which is located in the south of Brazil, in the state of Santa Catarina. The surface area of this watershed is about 15,000 square kilometers. Its main stream length is about 280 kilometers. It's the Itajaí River. The population inside the watershed is estimated on 1.2 million people, and there are over 60 towns inside the watershed. It's a very important watershed for the economy of the state of Santa Catarina, and a lot of land use changes happen over the years. The main objective of this study was to check if these changes on the land use were affecting the water balance in the watershed. So for the land use changes in the watershed, we used the software TerSet, and this software was also used to simulate a land use map for the year 2027 using neural network. And for the water balance simulations, the software SWAT was used. So it was used to simulate the water balance on the year 2027, and the results were compared with the year 2000. So as input data, we have precipitation, weather data, and river flow, daily data for this data. And we have the digital elevation model with the resolution of 10 meters. We had a pedology map and land use maps with resolution of 30 meters from the years 2000 to 2015. For the precipitation, we got data from 37 rain gauges inside the watershed and 23 rain gauges outside the watershed. 22 rain gauges were selected inside the watershed, and daily data was collected from the year 1997 to 2006. And the data from the rain gauges located outside the watershed and the rain gauges inside the watershed that were not used in the simulations, they were used to calculate the missing data in the selected rain gauges. And the missing data was estimated using the IDW method. For weather data, we collected data from 4 weather stations distributed along the watershed. The daily data was collected from 1997 to 2006 and from 2010 to 2018. And data collected was temperature, relative humidity, dew point, wind speed, solar radiation, and precipitation. For flow data, we collected data from 19 flow gauges, daily data from 1999 to 2006. And for the land use maps, we collected maps from the Map Biomas project. The maps have a resolution of 30 meters, and the land use maps were from the years 2000 and 2010 for the calibration of TerSet, and from 2015 for validation. So there were 3 evaluated scenarios in this study. First, the calibration and cross-validation scenario, which considered data from the years 2000 to 2004 and the land use map from the year 2000. We have the validation scenario, which considered precipitation data from 2005 to 2006 with the land use map of 2000. And finally, the 2027 land use map scenario, which considered the same data as the calibration scenario, so from the year 2000 to 2004, with the land use map of 2027. And for the model efficiency, we used the KGE coefficient, which is a fairly new coefficient. It's being used a lot in hydrological studies. And in case if you're interested, I can send you later by email some papers on this coefficient. You please just ask me in the chat here of the webinar, and then I can send you later some papers. So for the calibration, we had 6 steps using data from 13 flow gauges. So here in this picture, we can see the steps. So the blue watersheds here, they were calibrated in the first step, and the orange watersheds, they were calibrated in the second step, and so on. We also made a sensibility analysis, and then after that, we selected 10 parameters for the calibration, and we could see that most of the parameters were related with characteristics of the soil, for example, curve number, soil evaporation compensation factor, groundwater revap coefficient, threshold depth of water in the shallow aquifer required for return flow to occur, available water capacity, and the cross-validation considered data from 6 flow gauges, which are represented by the black dots here in this picture. The validation considered data from all the 19 flow gauges, and here finally we have the results for this scenario. So for the calibration, we got a mean KGE of 0.76. In the cross-validation, we got 0.77, and for the validation, we got 0.63. So this graph here shows the calibration results for the flow gauge located more downstream in the watershed. And we can see that the observed data, blue line here, is walking very close to the best simulation result, which is the red line here. Even like if we look at the base flow, it gets very close here. And also in the peaks here, the lines are very close. So we got very good results here for the calibration. And here we have the results for the land use maps. On the left, we have the land use map for the year 2000, and on the right, we have the land use map for the year 2027, simulated by the software TerraSet. What we saw here when comparing both maps was that the biggest difference was found in the land use for planted forest, represented here by the color orange. In 2000, planted forest represented only 1% of the total surface of the watershed. And in 2027, it is expected that planted forest is going to represent 11% of the total surface. And we can see that most of the changes are going to happen on the subbasins located upstream of the watershed. For example, here in this region, in the north area, where we didn't see a lot of areas for planted forest. In 2027, it's expected that we're going to have a lot of planted forest. And here, when we see at the results that we got from SWAT, where we compared the water balance between the two scenarios, the scenario with the land use map of 2000 and the scenario with the land use map of 2027, when we look at the whole watershed, we saw a mean reduction of 4% on the aquifer recharge. And when we look at the subbasins individually, here we highlighted the 5 subbasins where we saw the biggest differences in the water balance. So here we got a mean reduction of 13% on the aquifer recharge. And in average, planted forest jumped from 2% to 19% of the total surface on these 5 subbasins here. So in conclusion, what we saw was that the growth on planted forest represented a reduction on aquifer recharge in these subbasins here. And that goes well with what we see in the literature, because there are studies that compares planted forest area with natural forests. And what these studies tell us is that planted forests have bigger evapotranspiration and surface runoff. That's what we got here in this study here, because when we look at the results that we got from SWAT, we saw that this reduction here on aquifer recharge was transferred to a bigger evapotranspiration and a bigger surface runoff. And what we see here also is that the integrated model is important if we are going to, for example, study here the groundwater of this watershed in the long term. It's going to be essential to use an integrated model. If we use a pure hydrogeological model, we are not going to be able to see these changes in the aquifer recharge along the years. If we use the integrated model, can get these changes. And the same, if we want to study only the surface, if we use a hydrological model, it's not going to predict well the exchange between the streams and the groundwater, because if we have less aquifer recharge, it means we're going to have less groundwater, and then we're going to have less changes between stream and groundwater. and this will affect directly the base flow, and the hydrological models, they can't predict this. So if we use an integrated model, we could be able to see these interactions. So now back to the integrated modeling. I'm going to show you a comparison between two softwares of integrated modeling. And I chose to talk about a commercial software and a free software. For commercial software, we're going to talk about MIKE-SHE, and for free software, we're going to talk about SWAT-MODFLOW, which is an integration between two of the most famous free softwares used for hydrology and hydrogeology. So the first difference is that you have to pay for the license of MIKE-SHE, and SWAT-MODFLOW, the license is free. It's a free software. MIKE-SHE has a user-friendly interface. It's easier to work with input data, and it has a better output data visualization. On the other hand, SWAT-MODFLOW has a really simple interface, and data entry and software integration is really hard depending on the area that you are working. MIKE-SHE is a distributed model, while SWAT-MODFLOW is semi-distributed for SWAT and distributed for MODFLOW. For the surface calculations on evapotranspiration, MIKE-SHE uses Christensen and Jensen, or Ian and Smith, while SWAT-MODFLOW uses Penman, Monte, Frisley-Taylor, or Hargreaves. And the choice between these different methodologies depends on the region you are studying, depends on the input data that you have. And there are some studies in the literature comparing the performance of MIKE-SHE and SWAT-MODFLOW for evapotranspiration, and there are not big differences. They are pretty much the same. Depends a lot on the region that you're studying, but there's slightly better results found for MIKE-SHE. For surface runoff, MIKE-SHE uses the equations of Saint-Venant or Manning, while SWAT-MODFLOW uses the SES curve number or Green and M. And again, both have good results. And in the literature, what we find is that MIKE-SHE gets slightly better results, but they're both good. In the unsaturated zone is where we get the biggest differences between these two softwares. In SWAT-MODFLOW, it divides the soil layers in two layers. So the first is the root zone, where the calculations are done by the equations of Sloan et al. And the layer between the root zone and the water table is calculated by the Richards simplified equations using the UZ-F1 package. And in MIKE-SHE, it depends on the kind of simulation that you choose and depends on your hardware. So if you want a faster simulation, you can choose the 2 layers option. And then with this option, MIKE-SHE uses the equations of Ian and Smith. You can choose the 1 layer option, and this uses the gravity flow. Or if you have a good hardware, you choose the multi-layers that use the Richards equation and gives you better results. And there's another big difference here between the SWAT-MODFLOW and MIKE-SHE in the unsaturated zone. As I just said before, in SWAT-MODFLOW, we have a division in 2 layers, the unsaturated zone between the root zone and the layer between the root zone and the water table. So in this unsaturated zone here for MIKE-SHE, it considers only the vertical flow. It's only the flow that goes from up to the bottom. It's only the vertical flow here for the infiltrated water. While in the SWAT-MODFLOW, in the root zone, it considers both the vertical flow and the lateral flow. This is in the lateral flow considers the water that goes straight to the stream. So the water infiltrates and goes straight through the streams. It doesn't go to the aquifer. In the layer between the root zone and the water table, SWAT-MODFLOW is the same as MIKE-SHE, only vertical flow here. That's a big difference between both models. And it's also important to notice that in SWAT-MODFLOW, in the root zone is the SWAT model that is making the calculations. The MODFLOW enters in this model only in the layer between the root zone and the water table. So from here down is where MODFLOW enters in the simulations. And for the saturated zone, both models use the 3-dimensional Darcy equation. So MIKE-SHE uses the Darcy equation, and in the saturated zone is where the MODFLOW comes to, and it uses the Darcy equation. So just to recall, here we have a picture that shows everything you can simulate with MIKE-SHE. You can see that pretty much you can simulate the whole water cycle. You can simulate precipitation, surface runoff, evapotranspiration, the groundwater flow, unsaturated flow, and same with SWAT-MODFLOW. You can simulate the whole water cycle, precipitation, evapotranspiration, groundwater flow. And the question that everybody's probably asking is, which one is better? It's a very hard question to answer because it depends a lot on the objective of your study, and also depends on how much money you have to spend on the project. Because as I said before, MIKE-SHE is a commercial software, so you have to pay for the license, while SWAT-MODFLOW is a free software. MIKE-SHE is much easier to use comparing to SWAT-MODFLOW, mainly due to the user-friendly interface that it has. I'm not saying here that MIKE-SHE is easy to use. No, it's not easy, but when you compare with SWAT-MODFLOW, it's much easier. And I'm saying it's not easy because you have a lot of different input data. You're dealing with a lot of different factors and physical processes. So you have to know what you're doing. Even though the interface is a friendly user, it's not easy to work with it, but it's easier when you compare with SWAT-MODFLOW. Comparing the accuracy of the results, they are both very good models. You can see a lot of papers in the literature that show that both SWAT-MODFLOW and MIKE-SHE have very good results. But when you compare both of them in general, MIKE-SHE is slightly better. It has slightly better results when comparing to SWAT-MODFLOW. Hardware requirements, you can say that both are the same. MIKE-SHE, if you choose the multi-layer for the unsaturated zone, you need a better hardware, but you have other options. You don't have to use the Richards equation for the unsaturated zone. So we can say that talking about hardware requirements, they are both equal. And for output data visualization, MIKE-SHE is much better. It has an interface for that, so it's much better to see the output with MIKE-SHE. One very important thing to have in mind when choosing between SWAT-MODFLOW and MIKE-SHE is that you cannot only look at the money you're going to spend for the license if you choose MIKE-SHE, because even you're going to spend money for the license, but you're going to save a lot of time working with MIKE-SHE because it's much easier to use and it's easier to start using it for the input data. If you choose SWAT-MODFLOW, you're going to spend a lot of time putting everything together. It's a time that you don't spend with MIKE-SHE. So if you think that time is money, you need to put that in your decision, because even though with SWAT-MODFLOW you don't spend money with the license, you spend a lot of time to get the model ready to run. So it's very important to have that in your mind. So coming to the conclusion of our webinar, first, it's always important to have in mind that the choice between models depends on the study objective and also on the availability of your data. Sometimes it's going to be better if you can use an integrated model, but you don't have any input data for example, your groundwater environment. So you're not going to be able to use an integrated model. You're going to be able to use only the hydrological model. So it's always important to have in mind that to use an integrated model, you need to have a lot of input data. Depending on the objective of your study, it is essential to use an integrated model. So for example, if your study involves a big range of time series, you're going to have much better results if you use integrated models. So for example, here I show you a graph that I got from a paper from Kim. He compared the use of SWAT and SWAT-MODFLOW in an area with the same input data, same period. And we can see that using only SWAT, the prediction for the base flow was much lower. And that's because with integrated model, you can have much more reliable results for the base flow. If you use only a hydrological model, you're going to probably underestimate the base flow. And that's what we see here. Now, the red line here shows the results for obtained with SWAT. And here on the base flow, you can see that you have much lower results comparing to the use of SWAT-MODFLOW. If your study involves a long-term basis, so here, for example, you have 2 years, basically 2 years of results, and you can already see the difference between the results of integrated model and hydrological model. So you have much more reliable results if you use integrated model. Also, it's important to have in mind that integrated modeling is challenging and it involves different fields of study, and you need a lot of input data, and you need time to study the area. You need time to study your input data, because you cannot have very good input data for your surface, but bad data for your underground environment, because one is going to affect the other. You really need to have good quality of input data and a good amount of input data. It's always also important to have in mind the points that just discussed between the differences of commercial software and free software. Yes, you spend less money if you choose a free software, but you're probably going to spend much more time to get your results. And using integrated models, you can get better results on aquifer recharge. So if your study involves hydrogeology and it's a long-term analysis, you're probably going to get much better results if you use an integrated model, because aquifer recharge is a very important input data for hydrogeological models. Finally, before finishing this webinar, I would like to show you again this famous picture of the water cycle, because I think it's very important to have in mind that the water works in cycle. You cannot study only the surface without looking with what's happening underground. And you cannot study what's happening underground without looking at what happens on the surface. It's all integrated. So that's why it's really important that we start using more the integrated models, because we're going to have much better results in our studies. So it's very important to have in mind this water cycle picture here. Always remember that water works in a cycle and you cannot separate the environments.